So just to wrap up exponential growth and decay, I want to say a little bit about graphs that we've seen. You don't really need to graph these functions to do the problem, so you don't have to study this video if you don't like to. But I just want to give a little bit of an explanation for the graph. There's a graph of exponential growth on one page of the handout, and then the second page has an exponential decay graph. And I would wonder, if I were a student, how does this e to the k t business relate to our earlier graphs of exponential functions that we saw at the beginning of this chapter? So I just want to say a little bit more. So here's just an example of an exponential growth function. F of t equals 3 e to the 2t. So I picked a real simple a03, k is 2. K is positive, so because k is positive, we know this is exponential growth. Now, this function, this exponential expression, e to the 2t, let's just look at the e to the 2t. E to the 2t could also be written as e squared to the t power by properties of exponents, because e squared to the t is the same as e to the 2t. That's one of the basic properties of exponents. So our function here, f of t, could be written as 3e squared to the t power, okay? And we can think of e squared as a number in its own right, right? I'm going to go to my calculator here. E squared is about 7.389. So that's that same function. Now there's no e here. I can write that same function using the base 7.389. This looks like the form a times b to the t power, where the base b is 7.389. That's a base greater than 1. And we know when the base is greater than 1, the exponential graph is going to be shaped like so. So there is a connection between this f of t equals a0 e to the kt, where k is greater than 0, and this f of t equals a times b to the t. They both have the same, they're the same function actually, same functions, with a graph that's like this rising up to the right exponential function. Here's x, here's y. And in applications, what I pointed out on the handout is often only the first quadrant, or the portion to the right of the y-axis, has relevance. Now what happens when k is negative? Here's another example. F of t equals 3e to the minus 2t. So k is negative 2 here. The e to the minus 2t I can think of as e to the minus 2 to the t power again. So I can rewrite that function f of t as 3e to the minus 2 to the t. And if I take e to the minus 2 on my calculator, I get that that's about 0.135. So this function is f of t equals, this function could be written as f of t equals 3 to the 0.135 t, which is the a times b to the t form again that we've seen before. My base b here, though, is 0.135. That's less than 1. So we have a base that's between 0 and 1. And when we graphed our exponential functions back in the first section, when the base was between 0 and 1, that's when we got a shape of the graph that was like so, right? Where the graph is coming down, approaching the x-axis to the right. And so this is f of t equals a0 e to the kt when k is negative, less than 0, is one way to think of this kind of function. And this form here is the a times b to the t, where the b base is just this number between 0 and 1. So this is just a way to understand why these base e functions with a k involved have a graph shaped like so, if k is positive, or like so, if k is negative. In both cases, probably in an application, only the portion to the right of the y-axis has relevance. And that's it.